Section 3.3 will focus on a physical property called density. Thinking about our airbags, do we want high or low density? Density is defined as the ratio of mass to volume of sample. Basically, we're looking at how heavy is the sample for its size. If we compare lead to air, lead has high density. If we take a very small sample, we will notice that it's very heavy. If we compare that to air, a large sample would have very little mass. The equation for density is found in the center of the page. It is also on your reference sheet. M stands for mass, and one of the most common units for mass is the gram. Be on alert for other units such as kilograms, milligrams, etc. V stands for volume. The most common unit here is the milliliter. Sometimes you'll see the centimeter cubed to represent a milliliter in terms of length. And then, of course, the liter would be a larger version of volume. Density is a ratio of mass compared to volume. So don't be surprised that you see two units for density. Grams per liter, grams per milliliter. You could have grams per centimeters cubed. You could even have something like kilograms per liter. An object floating in another substance signals that that substance is less dense than the other. If we take a look at the example to the right, you will notice that vegetable oil is sitting on top of water. So we would say that water is more dense than vegetable oil. However, if we're comparing water to corn syrup, we would then say that water is less dense than corn syrup because it's floating on top of the corn syrup. If we take a look at the diagram to the right, you will notice that the substance that sits on top is going to be less dense. There will be fewer particles in the same amount of space. You can see here that there's only 5 particles. The more dense area will be more crowded. They will have more particles in the same amount of space. And so in this case right here, we can see that there are 7. You can use the quantitative values of density to determine which substances are more or less dense as well. If we take a look at the chart on the left, you will notice that gold has a density of 19.3 grams per centimeters cubed. If I was to place gold in water, which only has a density of 1 gram per centimeters cubed, we would find that the gold would sink to the bottom. It is more dense than water. If we were to take a look at water and ice, we would also see very clearly that ice is less dense than water, and so it would float on top of the water in which it does. If we look at the diagram on the right, you can see that there are layers of liquids, of corn syrup, dish soap, water, vegetable oil, and rubbing alcohol. Notice that the most dense, the lowest layer, is the corn syrup. It has a value of 1.33 grams per milliliter, where the isopropyl alcohol will be 0.85 grams per milliliter, thus the lightest in density and the one that's going to be floating on the top. So how does density vary with temperature? Well, most substances will expand when heated. That increases the volume and decreases the density. You can see that in the scenario that I've drawn above. The mass stays the same at 5 grams, and as I change from a solid to a liquid to a gas, adding heat causes those molecules to break free from each other. The volume increases, and so you can see that the density is decreasing along the way. But water is an exception. As water is cooled, it expands, increasing the volume and decreasing the density. So when we're talking about solid versus liquid versus gas of water, we're going to find that the gas is still going to be the least dense, but the liquid will be the most dense, and the solid will be in between. Thus, ice is less dense than water. In order to calculate density, you will need to know the volume of your substance. Now, sometimes substances will have a definite shape, and you can use formulas like length times width times height to calculate that volume. But sometimes your substances will have an indefinite shape, and you're going to have to use a technique called water displacement. In this technique, you will record the volume of a liquid, in this case water, initially. You will drop the object or the substance into the graduated cylinder, and then you will record the new volume. If you subtract the difference of the final volume and the initial volume, you will actually get the volume of that object or substance. So if we take a look at the example on this slide, we have a dinosaur and we have a graduated cylinder that has a volume of 4.8 milliliters. If I take that dinosaur and I drop it in the graduated cylinder, it will take up some of the space of the water in that graduated cylinder, and it will cause the water to displace to a volume of 5.6 milliliters. If I subtract the difference, I will get a volume of 0.8 milliliters. So we would say that the volume of the dinosaur is 0.8 milliliters. Let's do a couple of problems. Example 1 is asking to solve for density. You have a sample with a mass of 2.50 grams and a volume of 1.7 milliliters. So we're going to use the equation D is equal to m over v, and we'll substitute in the values for the variable. So 2.50 over 1.7 milliliters. We're going to put that into the calculator, and that will give me a number of 1.47058, and we can go on and on, grams per milliliter. We want to go back to our significant figure rules. We know that we've got 3 sig figs on the top, only 2 on the bottom, which means we only want to have 2 sig figs in our answer. That would bring me to the 4. The 7 is larger than 5, so my answer is really going to be 1.5 grams per milliliter for the density of this sample. In this example, we're solving for mass. They tell you that you have a volume of 2.34 milliliters and that the density is 2.78 grams per milliliter. So in this case, I'm going to go back to that same equation. Density is equal to mass over volume. I can go ahead and plug in the numbers. And do my math. In this case, I'm going to cross multiply. Just put that over 1. And I'll get mass is equal to 6.5052 grams. Once again, if I go back to my starting values, they both have 3 sig figs, so I want my answer to be 3 sig figs. That 5 is going to change that 0, and my answer is really 6.51 grams. Now you could manipulate the equation before plugging in the values, and in that case, if you looked at the equation over here, we would say that mass is equal to V times D. Our last example is solving for volume, and it looks like they give you a mass of 45.4 grams and a density of 0.87 grams per milliliter. We're going to go back to that same equation. D is equal to m over v. We're going to plug in the information. And we're going to solve algebraically. Once again, I'm going to go put this over a 1. I'm going to cross multiply. I'm going to get 0.87 grams per milliliter. V is equal to 45.4 grams. And I'm going to divide both sides to get V by itself by 0.87 grams per milliliter. That will give me a volume of 52.1839. Notice that the grams cancel out and leave me with milliliters. If I go back and I look at my starting substances, 2 is the smallest number of sig figs, so I'm really going to go to the second significant digit. That 1 is not large enough, and so 52 milliliters is going to be my answer. Once again, you could go ahead and solve this algebraically at first. This would give you m is equal to VD, and then you could divide both sides by D to get volume, and then just do that direct plug and chug. It's whatever you feel most comfortable with. All right, if we take a look at the mass, which is 612 grams, and the volume of 345 centimeters cubed, and we divide the mass by the volume, you will get a density of 1.77 grams per centimeters cubed. Now we've said the accepted value of aluminum's density is 2.70 grams per centimeters cubed. Because these numbers are not the same, we would say that no, this sample is not aluminum. Remember that density is a physical property, and it's actually an intensive property. As the mass will increase, so will the volume in the same proportional ratio. So whether you are looking at a small sample of aluminum or a large sample of aluminum, the density should always be the same. The last thing I want to mention is that we can actually graph density. If you had many samples of a substance, and you were able to measure the mass and the volume of each of those samples and plot them on a graph, you would actually get some data points that would follow a straight line. And that's because density is a directly proportional relationship. Okay? If we were to take the slope of that line, which is the change in the rise over the run, you would then actually get the density of that sample. We will do something very similar to this in class. And this concludes density and its calculations.